Are we live? Let's see. We are. Okay. Okay. So, time to lock in. Yeah, I needed to grab my laptop. Let's see. If I go to CDs. Okay. Fully. So I did all the work in my laptop, but I didn't push it to my GitHub. So on my Mac, I didn't have the updated code. So hopefully, I just pushed it right now. Hopefully, I can just pull from there and we can get started. Let's see. Okay, cool. Seems like it's working. Mm-hmm. Okay, let me change the source. Application capture. Let's do spider. There we go. Cool. Okay, so this is what problem set 2 of MIT 6100B course. This involves finding the shortest distance on an on the MIT campus, right? So this is like a map that we're given. This is a node. This is another node. So we have to connect an edge from this node to this node. This is the distance. This is the total distance between node 32 and node 36, and then 0 is basically the distance that we spend outside, right? So there's a total distance and there's an outside distance, right? And then I did like the first two parts of the problem, which is creating the whole graph structure. So this is the entire graph structure. This class represents the node, this is edge, this is the weighted edge. So if we have these weights attached to it, right, you can see that we have the total distance here and then the outdoor distance, and then this is me creating the graph basically, right? And then there's like a lot of other test cases which they all pass, and then this is me testing it with my own map that I created. So we have node A, node B, the total distance is 10, 9 of which has to be spent outdoors, right? Now we need to do the third part of the problem set, which is I think the DFS algorithm itself, or the BFS algorithm. So let's do that. So right now, let's see. Yep. Okay. So let's read the problem. And this is just me asking if my code is correct or not to Claude. Okay, so we can define a valid path from a given start to end node in a graph as an ordered sequence of nodes n1, n2, nk. So 1, 2, 3, 5, 4 is an ordered sequence, right? And there is an edge from n of I to n of I plus 1 for I equals 1 to k minus 1. Okay. In figure 2, each edge is unweighted, so you can assume that each edge has a distance 1 and the total distance on the path is 4. So 1, 2, 3, 4. Okay. In our campus map problem, the total distance traveled on a path. Let me just set an alarm at 8:45. So I have class at 9 a.m. so I have to leave at 8:45. But let's keep coding till then. Okay. So in our campus map problem, the total distance traveled on a path is equal to the sum of all total distances traveled between adjacent nodes on this path. Total distance traveled on a path is equal to the sum of all total distance traveled on that. Similarly, the distance spent outdoors on the path is equal to the sum of all distances spent outdoors on the edges in the path. Fair enough. Depending on the number of nodes and edges in a graph, there can be multiple valid paths from one node to another, which may consist of varying distance. We define the shortest path between two nodes to be the path with the least total distance traveled. You're trying to minimize the difference traveled while not exceeding the maximum distance outdoors. How do we find a path in the graph? Work off the depth first traversal algorithm covered in the lecture to discover each of the nodes and their children nodes to build up possible paths. Note that you'll have to adapt the algorithm to fit this problem. Read more about depth first search here. The link. There is no link, but we can just Google it up, right? Problem 3. Write a sentence describing what the objective function for this problem. What are the constraints? Okay, let's switch back to Spider. I don't know if there's a neater way for me to do this, so I don't want to share my entire screen, but at the same time I don't mind sharing Safari and Spider both at the same time. I'm new to streaming. Okay, so my objective function is let's see, what is my objective function? It is to get to full screen, entire screen. Yep. Okay. Is to what is my objective here? It's basically to go from my starting node to the goal node, right? Okay, that is my objective function. And then my constraint is to do that in the shortest possible path, i.e. the path that has the least amount of weight, right? Okay, let's see. So I'm just gonna ask Claude if it likes my answer. This is how I use AI. I just make it double check my work, because I might be wrong, right? And Claude might be wrong as well, but like it can give me ideas and then I can verify it, right? But I'm pretty sure Claude is smarter than me, at least on intro level courses. Like there's no way there's no way I'm better than Claude. So usually ask it to act like my professor or TA, so that it doesn't just outright give me the answer, but it I don't know, guides me towards the answer. Okay, so apparently I was wrong. So Claude says that objective function is what are you trying to minimize or maximize. So yeah, so my objective function is to go from my starting node to the goal node using the shortest possible distance, right? What limits must you stay within? That's the constraint. So did they give us any limits for problem 3 as long as we're inside the graph? So okay, so we're trying to minimize the distance while not exceeding the maximum distance outdoors. That's something that I read. While keeping the outdoors that could be the constraint, right? So the constraint is we are trying to minimize the distance traveled. We are trying to minimize the distance traveled while not exceeding the maximum distance outdoors. Let's see what Claude thinks of this answer. It says I can make the first part shorter, um, but that's nitpicking, I guess. So we're ready to do the next part of the problem, which is 3b. Okay, let's see. Let me try to switch. I think this is better, right? Okay. Spider to Safari. There we go. Okay. Implement the helper function. Implement the helper function get underscore best path. Assume that any variables you need have been set correctly in the directed DFS. Below is some pseudocode to help you get started. Okay, if start and end are not valid nodes, raise an error. Fair enough. Else, if start and end are the same nodes, update the global variables appropriately. Else, for all the child nodes of start, construct a path including that node. Recursively solve the rest of the path from the child node to the end node. Return the shortest path. Okay, interesting. Graphs can contain cycles. A cycle occurs in a graph if the path of node leads you back to a node that was already visited in the graph. When building up possible paths, if you reach a cycle without knowing it, you could get stuck indefinitely by extending to the path with the same nodes that have already been added to the path, right? We can use a set for that, right? If you come across a path that is no longer that is longer than your shortest path found so far, then you know that this longer path cannot be your solution. So there is no point in continuing to traverse its children and discover all paths that contain this subpath. You must include this optimization in your solution in order to receive full credit. Okay. While not required, we strongly recommend that you use recursion to solve this problem. I think iteratively we do it with a while loop, right? I'm really bad at recursion, but let's try to do this. It's gonna take some time, but we're here to learn. So, oops, not OBS, Spider. There we go. Okay. So get best path. Okay, so it takes a digraph, the search, right? Okay, start string and building number at which to end path, list, names, total distance travel, and total distance outdoors. Turn the tuple. Okay. Let's see. Is there any way I can bring Safari as well? Because I'm gonna draw a lot in Safari right now, and then might as well let you guys see that, right? It's just me right now, so. Eh. There we go. Okay. Browser, add existing, create new. Nope. Remove browser. Yes, please. Okay. Unlucky, I guess. I gotta Google that up later. Okay. So if we do there we go. Application capture, Safari. Okay. There we go. So we have this and then okay, so we have Safari here. Okay, and then if we do this, nice. Okay. Brilliant. Now let's try to solve this problem. So you can write the first line of code pretty easily. If start so start and end are a string. Okay, right? So that parameter is a string. So let's do it one step at a time. Let's try to do the error checking at first, since we are already given a pseudocode, right? Say start and end are not valid nodes. So it says update the global variables appropriately. So I'm pretty sure we're gonna have to write a function within a function. And the global variables would be my max distance outdoors, and it's gonna be my best path as well, right? Okay, so my start and end are always gonna be the same, right? Well, not necessarily. If I solve this recursively, no, I think I'm gonna start and end is gonna be the same if I think about it. What is it gonna be? So let's say if we have A as a node, this goes to B, right? And then let's see if they gave us any examples here. Okay, yeah, we have 1, 2, 3. I mean, this just has only one path though, right? Although I know it from 1 or from 2 it can go to 1 and 3, but realistically speaking, this is, I think, a better example, right? And we're dealing with digraphs, so it's gonna have directions. So I'm just gonna screen capture this. paste it in Canva, and then yeah, analyze. Okay, so let's see, how would this work, right? Okay, so we have A and then F as the goal node. So A start and F as the goal node. Okay. So from A we can go to B and then C. So so we have our path here. So we're gonna have our path, and that's gonna be a list of strings, right? Comma int, comma int. Total distance outdoors. Okay, so total distance travels, total distance outdoors. So at first it's gonna be A, right? And from A we can go to so we're gonna basically loop through all the child node of A. So we're gonna have B and C, right? And then I'm trying to think of what function to call. So and then we're gonna call that function, right, for the rest of the path. So my best distance is gonna be whatever my max distance is minus that. You're gonna have to change your start, and when my start equals to my end, that's when we return, right? Yep. That's how recursively we're gonna get shorter and shorter paths. Okay, let's try to solve this. I think I have a baseline understanding on what to write. Okay. So the first part is if start and end are not valid nodes, right? So before that we can write df helper, right? And what's by okay, my helper function will take a digraph. It should take all the values, right? Or do I need a helper function? Well, I need it because I need the path thing, right? Okay, so I have a helper function. So if there's a type, right? Okay, start is not equal to str or type path, not path, and is not equal to str. Raise type error. My start and end node must be of type string. Else if start equals end. Okay, so this is when I've reached a valid path, right? My best underscore path. So I don't need best underscore path here, or do I? Let me think about it. think so I need it because I will update the global best underscore path dot append path, whatever path we're exploring right now, right? And path is gonna be so, and then we can do best underscore dist is to path 1, right? And then I don't think so we need best underscore dist. Or honestly, we don't even need max underscore dist outdoors. We definitely do need the end though. So end, right? Okay, now the recursive step. Okay, else now let's see, for all the child nodes of start, right? So let me try to remember how my graph again. So I mean I can do digraph dot edges, right? However, is this the best way to do that? So I can do digraph dot edges, and that's basically gonna be AB 10.9 and then AC 12.2, BC 1.1, right? Something like that. If I do it's gonna be, so A can go to B and then it can go to C, right? Let's see if there's other ways to do this. Okay, so there's get edges for node. We have this method. So we can use this method. That way we're not directly accessing the internals, right? Okay. So let's see. Edges equals to digraph dot get edges underscore for node. And then we're gonna start here, right? And the reason being, please expect a string as a node or a node as a node. I forgot. I think it expects a node as a node, not a string as a node. So node start. Okay. So we have the edges, right? So now we can do, so for each edge we get three things. So we get four things actually. Start, comma, I'll just write it S, comma E, comma D, and then comma O in edges, right? And then path including that node, path, okay, so we can do if O greater than max underscore dist outdoors. We don't need that path, we can continue. And then, right, same goes for if we have a path here. I'm trying to understand the data structure of path. It's a list of strings intended to the current path of the nodes being traversed. Okay. So for the path, right? Let me just open the Safari. So let's see. So we have A, right? So the data structure is gonna look something like this. So for A, we're gonna have A, comma B, comma 15, comma 10, right? And then we're gonna have, this is what we're gonna iterate over, right? A, comma C, comma 14, comma 6. Now let's see. So one possible path. So just get best path, right? So for path we can have A, comma B, comma comma 15, right? Well, actually no, it's a list of strings, so it's gonna be A, comma B, comma A, comma B, 15, comma 10. So ideally that's where we want to keep it at, right? And then make B the start, right? And then keep doing that, and then make E the start, and then keep doing that, and then we can make C the start. But then we'll see we get nowhere with that, right? And then we can have a set, and inside the set, if we already explored something, we can just choose not to explore it, so that way we don't get the cycle. And for the set, do we keep it in the helper function or the global function? Well, the helper function, right? Because yeah, because we don't want to keep it in the global function because we're gonna have to explore. Okay. But we'll think about the set a bit later, but I think for now this idea is not that bad. If path 1 greater than best underscore dist, right? And we continue. Else helper, right? We have our digraph. Our start is gonna be our E, right? T, comma O. And then my bad, bro. What am I doing? Our path is gonna be our path. And we're gonna keep supplying our end. And in here we're gonna append F E comma right, comma total distance, outdoor distance, right? And then in here we can call once the loop is done, we can turn path. And here we can call test equals to helper digraph start path end, right? We can print that out maybe. This is gonna give me a bit. Print the tuple out. If this is correct, then we can basically but I'm pretty sure there's bugs in here. But even if there's any bug, I'm pretty sure like we're pretty close to the implementation that we want to get. I think we have to break here instead of continue. Let's see. So we have test path, right? And then there's directed DFS, and then there's this. I don't know if test path. I think it might probably does test both of them, right? And here it's doing the directed DFS test. Yeah. Well, we can write our own test case. Let's see. Let's write something. Let's use this one. So what is this one? Let's use this one, and then we can write a better test case later. So let's visualize this, right? Okay, then we can just use this one. For this we have 3 nodes A, B, and C, right? Okay. So to go from A to B, 10 is the total distance, 9 is D, and then from A to C, 12 is the total distance, and then from B to C, 1 is okay. So this is actually a pretty good test case. So it should return us 11, right? 11. Yeah. With 9 being the output distance to walk. Okay, so let's see. I think I already wrote this function at the beginning for the digraph thing, right? Well, we can just use this, honestly. Yeah. Let's see. So we have load underscore map. So d equals load underscore map load load underscore map underscore test dot txt, right? And then yeah, start equals a. We can definitely write more error checks here now that I think about it. N equals C, right? Path is gonna be empty at first. Max underscore. I don't care about this. Let's just say 100 for now, and then for now I think test underscore ust is 0, and then test underscore path is empty list, right? And then we can do not helper. What do you call that? Get underscore best path. Yeah, just name this digraph, and then yeah, should be chilling. Okay, let's see how wrong we are. Method object is not subscriptable. Let me grab some water. Subscriptable. Okay, let's see. This falls over. Okay. Digraph dot get underscore edges for node. Oh, yeah. I meant this. Okay. It returns as an object of weighted edge. Okay. That's a bummer. Let's see if we print edges. There's no way it's printing out the object because there's a string method defined for weighted weighted edges. So it shouldn't print out the default object str method. What's weird is this is fine. Why would it do that? Very weird. I wanna just try something out. Yeah, this doesn't work. Because it should be a node. Yeah, exactly. It should be a node. How much I do understand. It's returning me a weighted edge object that I also understand. What I don't understand is why am I getting this instead of you know, the normal str method that I defined, which it should give me the normal str method. Let's see, maybe if we do whoops, I erased everything. Bummer. I have it on my GitHub though, so that's fine. Let's see, graph.py. There we go. Okay. Okay. So all I'm saying is, instead of this, we can just do edge dot underscore str. Yep, and then yo, I didn't mean this, I meant call the method, right? Call the method. Missing self. Yeah. Yeah, okay. Now if we print this out, okay, it's still the fucking weighted object. Never mind, I thought I did something brilliant here. Apparently not. Let's see, the problem is that it's giving me weighted object and I can't iterate over weighted objects. I mean, the one thing that we can do is just iterate over the nodes directly, access the internals. But then why did I even write this function, right? I mean, it is following. It is a list of node, a list of edges. Let's see. So these are each edge object, right? So we have get source and then get destination, right? Sort. You can do get underscore source at e and underscore get destination, right? Then we have d equals edge dot get underscore total, what's the method called? Total distance, and there is output distance. Okay, total distance, and then all get output distance. Okay. Yes, sir. Int. Okay. List index is out of range. Of course it's out of range because there is no path 1. It just doesn't exist. we can just do this 0. Okay, now what? Now access local variable best underscore dist. It is not associated with the value. So when I said this best underscore dist, I don't mean to create a new one. I mean to update this one. But I'm guessing it's not understanding it. So for that, we can definitely call best underscore dist here, and then call it with best underscore dist. No. There we go. It's one argument now, isn't it? And then I don't need to do the tuple. Consider if it's offsetable. How are we looking, boys? What? Oh. Yeah. Okay. Start and end must be of type string. Size. So somewhere along the lines, it's not of type string anymore. It's some other type for some reason. I don't know how that works. Oh yeah. Oh, we have a digraph, right? And our end was our end, and then our best path is our best distance, and then I don't understand how. Okay, let's see. Perhaps I'm just dumb. Holy shit, I'm sleepy. Well, let's see. Okay. So let's run to this code. Let's see. Okay. So first our start is A, our end is C, right? So we enter our function. Type start is not they're both strings, they're not equal. Edges equals digraph, so or for our A we get edges. So the edges are a list, something that looks like this: 11, 8, and then A, C, 12, 2, right? And then we iterate. So we have this one right now, and then for this one we get all, we unpack it, and then we see it's not. So we append this to our path. So we do what we do is we append this and a comma b, right? 11 8 done. Okay, and then we call the function again. Okay, this time we have dot get underscore destination. Now perhaps what is this giving me? I'm sure these are yup, this is definitely of type node, isn't it? So I think let's try to foolproof that. Okay, so first of all, start and end, they have to be in my digraph. We will initially I think it's the expect a string. And there is no built-in conversion of type node type string, right? There's just we have get name. We have get underscore name. So get underscore name. Get underscore name. Int. Oh, this is very messy code, but we can clean it up later. Okay, let's see. Okay, we have something. What do we have? Compiles. We have AB 10.9 BC and then AC 12.2. So it's giving us basically all the path instead of the best path, right? Oh, yeah, of course. We don't want all the path, we want best underscore path. Now let's see. Okay, funnily enough. Okay, now we can maybe debug this better, because at least we are running product now. Sure, it's buggy, but it works. So we can fix our issues and then we can make the code significantly cleaner, because this is really bad code. I think in terms of complexity this is fine, like, but in terms of code style this is horrendous. But let's see. Holy. Okay, It's 8:35, so I have 10 more minutes before my class, and then after I come back from class, I'm gonna get back to it. I'm still gonna keep streaming though. I'm just gonna leave it paused. Okay, what did I do? Okay, so let's debug this whatever I output it. Okay, nice, we have something. Okay, so we call our helper function of type string. They are, so we go to, they're not, one is A, the other is C, right? So we have our edges. So for our edges, we have AB 11 8, and then AC 12 2, and then BC 1 1, right? This is, oh, we don't have BC, we have these two for now. Okay, I think the DFS is happening properly, because, well, not necessarily, because we're doing AB and then BC, but it should be AB. Yeah, the DFS is happening properly. We're going depth first, so AB, BE, right? EF. So it's just the way I'm printing it out. That's not proper, right? Yeah, because I think the DFS is happening properly. Although it's repeating a lot of work, we can cut down on that by using the set thing, I guess. But let's see. So for edge in edges, right? So we have our source. Our source here is A, and for the first one is B. Total distance is 11. Outdoor distance is 8, right? So actually, let me just, you gotta be safe, right? I need integer versions because I'm gonna be doing arithmetic on them. I know they're string, but I definitely need, okay, it doesn't change anything, but like, you know. Okay, so now we're comparing 8. If that, so our max outdoor is 100, so this is never gonna pass. It's not. If our path, so our path right now, the first variable is 0, so that is not, plus one major issue is that we're not even adding our total path, right? We're just doing per layer, so total 0 total see. Right. Why is there a linter here? What? It's outside. Can't it access the global variable? I need create global. Okay, so I need to write global total here. I swear, if this function is inside the helper, I should be able to do this without this much trouble. And it is, right? Yeah. Oh, it's time for my class. but I'll be back soon. To 1 minute. See. Let's see if I'm a professional streamer now. Image. There we go. I am so bad. Okay, we are back. I have a class in like 20 minutes, but I still have 20 more minutes. I feel like the best thing that I can do right now is to rewatch the last 30 minutes of the lecture video and then get back to the code because I feel like conceptually I have some issues. So I'm just gonna do that. Let's see. If I do this, Safari. Yep, I'm just gonna rewatch this.
Communication networks is another great example of a shortest path problem. You'd like your message to get you your friend as quickly as possible and not go as many times around the world before it gets there. So what's the shortest amount of time or the fewest links I have to use to get there? Lots of nice biological problems that also capture this piece. So here's an example. We're going to use this to look at two different kinds of algorithms to solve this problem. This is a little navigation problem from a set of cities. Think of it as flight paths. If you're from Arizona, my apologies, but once you get to Phoenix, you can't get out of there unless you grow from the ashes, I guess. But, you know, it's a way of dealing with how to get around in places. And to think about this, here's the representation that we'd have in the graph. The adjacency graph here, or adjacency list here is from Boston, I can get to Providence, I can get to New York. From Providence, I can get to Boston, I can get to New York. From New York, I can only get to Chicago. Chicago, I can go to Denver or Phoenix. Denver, I can go to Phoenix or New York. And from LA, you can only come back to Boston. And Phoenix has no exits out of it. So there's that representation. I just want to let you see that, right? There are the keys in the dictionary. They're all the nodes. And there, each one of those lists is a set of edges from the source to the destination. Okay. How would I build this? Well, this is the code I just ran. I just want to show it to you. I noticed, by the way, in the slides I distributed earlier, this missing, the return G is missing there. If you want to correct it, I'll repost it later on. I'm going to create a little function that's going to build a city graph. I'm going to pass in a type of graph, which I will then call to create it. So I could make this as a digraph. I could make it as a graph. I'm going to start off with it as a digraph. And then notice what I do here. I just run over a little loop with a set of names, creating a node with that name, and then adding it into the graph. Right? So node is a class instance that creates, or a class definition that creates an instance. And once I've got that, add node is a method on the graph. It will simply add it in. And then this set here is simply adding in the edges. And I can do that. I'm capturing what I had on that previous slide. I'm going to give a name to getNode. It will get out the actual node. And I use that coming out of the graph G. I do the same thing with the getNode from graph G for Providence. And then I make an edge out of that. And then I use the method from the graph to add the edge. If this looks like a lot of code, yeah, it's a lot of words, but it's pretty straightforward. I'm literally creating nodes with the names using the appropriate methods, creating an edge, adding it into the graph. And when I'm done, I'm just going to return the graph G. Okay, now I want to find shortest path. And I'm going to show you two techniques for doing this. First one's called depth first search. It's similar to something Professor Guttag showed you when you sort of took the leftmost depth first method in terms of a search tree. The one trick here is because I've got graphs, not trees, there are the potential for loops. So I'm simply going to keep track of what's in the path, and I'm never going to go back to a node that's already in the path. So I don't just run in circles going from New York to Boston to New York to Boston constantly. All right? So second thing I'm going to do here is I'm going to take advantage of a problem you've seen before, which is this is literally a version of divide and conquer. What does that mean? If I want to find a path from source node to destination node, if I can find a path to some intermediate node from source to intermediate, and then I find a path from intermediate to destination, the combination is obviously a path the entire way. So recursively, I can just break this down into simpler and simpler versions of that search problem. So here's the idea behind depth first search. Start off with that source node, that initial node. I'm going to look at all the edges that leave that node in some order, however order it was put into the system. And I'm going to follow the first edge. I'll check to see if I'm at the right location. If I am, I'm done. If I'm not, I'm going to follow the first edge out of that node. So I'm actually creating a little loop here. And I'm going to keep doing that until I either find the goal node or I run out of options. So let me show you an example. I've got a little search tree here, very simple one. There's my source, there's my destination. In depth first, I'm going to start at the source and go down the first path. See if I'm at the right place. I'm not. So I'm going to take the first path out of here, which might be that one. See if I'm in the right place. Actually, let me not do it that way. Let me do it this way. Am I in the right place? I'm not. So I'm going to take the first path out of this one, which gets me there. I'm still not in the right place, so I'm going to take the first path out of that one. And you can see why it's called depth first. I'm going as deep, if you like, in this graph as I can. From here to there, to there, to there, to there. At this stage, I'm stuck. There's no place to go to, so I'm going to go back to this node and say, is there another edge? Which in this case, there isn't, so I'll go back to here. There's not another edge. Go back to here. There is another edge, so I'm going to go this direction. And from here, I'll look down there. Again, notice I'm now going depth first down the next chain. There's nothing from here, I backtrack. There's nothing from there, I backtrack over to here. There's no additional choices there, so I'll go all the way back to here to follow that one. And then I'll go down this one again, backtrack, backtrack, and eventually I find the thing I'm looking for. Depth first, following my way down this path. So let's write the code for it. Yes, ma'am? So the question is which node or which edge do I choose? Is however I stored it in the system. So since it's a list, I'm going to just make that choice. I could have other ways of deciding it, but think of it as, yeah, essentially random, which one I would pick. Okay, let's look at the code. Don't panic. It's not as bad as it looks. It actually just captures that idea. Ignore for the moment this down here. It's just going to set it up. Depth first search, I'm going to give it a graph, a start node, an end node, and a path that got me to that start node, which initially is just going to be an empty list. Something that tells me what's the shortest path I've found so far, which would be my best solution, and then just a little flag here if I want to print out things along the way. What do? I set up path to add in the start node. So if path initially is an empty list, the first time around it's just here's the node I'm at. I print out some stuff and then I say, see if I'm done. I'm just going to stay at home. I'm not going to go anywhere. Not unlikely to happen, but you'll see recursively why this is going to be nice. If I'm not done, then notice the loop. I'm going to loop over all the children of the start node. Those are the edges I can reach, the nodes I can reach with a single edge. I pick the first one, and in answer to the question, in this case it would be the order in which I stored it in the list. I just pick that one up. I then say, let's make sure it's not already in the path, because I want to avoid loops. And assuming it isn't, and assuming I don't yet have a solution, or the best solution I have is smaller than what I've done so far, oh, cool. Just do the same search. So notice there's that nice recursion, right? I'm going to explore. I just picked the first option out of that first node, and the first thing I do is try and see if there's a path from that node using the same thing. So it's literally like I pick this one. I don't care about those other edges. I'm going to try and take this search down. When it comes back with a solution, as long as there is a solution, I'll say that's my best solution so far. Right? And then I go back around. Now, this last little piece here is just if, in fact, the node's already in the path, I'm just going to print something out that says don't keep doing it because you don't need to keep going on. And I'm going to do that loop, taking all the paths down until it comes back. And only at that stage do I go to the next portion around this loop. The piece down here just sets this up, calling it with an initial empty list for path and no solution for shortest. So it's just a nice way of putting a wrap around it that gets things started up. This may look a little funky. May look a little bit twisted. So let's see if it actually does what we'd expect it to. And to do that, I'm just going to build a little test function. I'm going to build that city graph. I'm just going to call shortest path. I'm going to print it out. And I'd like to see, is there a way to get from Boston to Chicago? So let's go back over to my Python and try that out. And I've got a call for that. Oh, and it prints out. I start off, oh, so I did it the wrong way. It's from Chicago to Boston. Yes, Chicago to Denver to Phoenix, from Denver to New York. Comes back and says, I've already visited. Basically concludes I can't get from Chicago to Boston. It's just printing out each stage. Let's actually look at that a little more carefully to see how it got there. So there's my example. There's the adjacency list, and here's what happens. I start off in Chicago, so that's my first node. From Chicago, the first edge goes to Denver. Denver's not what I'm looking for, but since I'm in Denver, recursively I'm going to call it again, so the first edge out of there is to Phoenix. Again, sorry if you're from Arizona and Phoenix, there's nowhere to go, so I'm going to have to backtrack, and that will take me back up to Denver, and I look at the next edge. Takes me to New York. From New York, I'd like to go to Chicago, but oh, that's nice, because remember that first check, it says, is Chicago already in the path? It is. I don't want to loop, because otherwise, I'm simply going to go around and around and around here, and it may be good for frequent flyer miles, but it's not a great way to get to where you're trying to go. So I break out of it, and now what else do I have left? Chicago to Denver, I've explored. I look at Chicago to Phoenix. From Phoenix, there's nowhere to go. I go back up to Chicago. There are no more paths. I'm done. Okay. Now, turns out you can actually get somewhere in this graph. So here's just another example. I'm simply going to show you if I want to go from Boston to Phoenix. Notice the set of stages. And you can see, notice how at each stage it tends to be growing. That's that depth first. I'm exploring the edges. I find a path. That's great. But is it the shortest path? I don't know. So having found that path, I try and take the next branch, which finds a loop, and I keep moving through this, finding paths until I look at all the possible paths and I actually return the shortest path. You can try running the code on it, but what I want you to see is again this idea that I can explore it, but in fact I'm going to have to explore it in a particular order. But there's depth first search. It will find a solution for me. Alternative is what's called breadth first search. Sounds almost the same. Again, I'm going to start off with initial load. I'm going to look at all the edges that leave that node in some order. I'm going to follow the first edge as before and see if I'm at the right place. If I'm not, I'm going to follow the next edge and do the same thing. So whereas this went down through the tree as deeply as I could of the graph, in breadth first, I'm going to start off taking that edge as before. I'm not done. I'm going to keep track of that in case I want to explore more of it, but I'm going to go back over here and follow that edge. I'm not done. Again, I'll keep track of that, but I'll come back up here and explore that one. And oh, cool. I found a solution in 3 steps. I reached the destination. And notice, because I'm exploring all the paths of length 1 before I get to paths of length 2, once I find a solution, I can stop, because I know it's the shortest path. Any other path through here would be longer than that particular solution. So the loop here is a little different. I'm looking over all the paths of length 1, then all the paths of length 2. And the one thing I'm going to have to do is I'm going to have to keep track of the remaining options here in case I have to come down to them. Because if I didn't find it at the first level, then I come down here and look at things of length 2. Okay? So let's build that code. Breadth first search, or BFS. Again, a graph, a start, and an end node, something that would just print things out as I go along. My initial path is just the start point. But now I've got to keep track of what are the paths that I have yet to explore. And so for that, I'm going to create something called a queue. And a queue is going to be a list of paths. Remember, a path is a list of nodes. A queue is going to be a list of paths. So the initial queue is just where I've started. And then as long as I've got something still to explore and I haven't found a solution, I'm going to pop off the queue the oldest element, the thing at the beginning. That's my temporary path. I'll print out some information about it. And then I'll grab the last element of that path. That's the last point in that path. And I'll now explore. Is it the thing I'm looking for? In which case I'm done. I'll return the path. Otherwise, for each node that you can reach from that point, create a new path by adding that on the end of this path and add it into the queue at the end of the queue. So I'm going to keep looping around here until I either find a solution here, which I'll return, and if I get through all of it, I'm going to return none. And right there, there's that nice thing where once I find a solution, I know it's the shortest thing, I can stop. Again, let's look at an example of this. So I'm going to go back over to Python where I've got a version of this. I'm going to comment that out. And down here in breadth first search, I've actually added a little piece of code that I don't have in the handout that's going to print out the queue as well so we can see what happens when we call this. So let's take a look at it. My initial call, there's one thing in the queue, it's just Boston. Started in Boston. So the best path, or the current path, is to start in Boston. I take that element off the queue and I say, what are the things I can reach from Boston? Oh, nice. I put two things in. I can get from Boston to Providence. I can get from Boston to New York. The top thing's gone off the queue. I popped it. I've replaced it with two things there. I take this and say, okay, from Boston to Providence, where can I get from Providence? Oh, I can get to New York, so I put that in the queue. This has gone off. That one is still there. And I do that because I haven't yet reached the thing I'm looking for, which was, I think, Phoenix I was trying to get to. And you can see at each stage, I'm taking the top thing off the queue, asking for all the things that I can get to, and adding them to it. And notice, in some cases, it may be more than one. For example, which one do I want here? Right here. If I take Boston, New York to Chicago. From Chicago, I can get to Denver. So there's one new path. I can also get to Phoenix. There's a second new path. Also notice how they're only growing slowly as I build them out. And in fact, if we go back, we can see that nicely by looking at what happens if we were to actually trace this along. So Boston to Phoenix. I start at Boston, and I look at that, and then that. Those are all the paths of length 1. Having exhausted those, oh, nice. I'm looking at paths of length 2, and then paths of length 3, and then paths of length 4 until I found the one that I wanted. And here's one other way of looking at it. Breadth first says I look at each path of length 1, and then, oh yes, I avoid the loop. I look at each path of length 2, then paths of length 3, until I actually find the solution. Subtle difference, different performance. Depth first, I'm always following the next available edge until I get stuck and I backtrack. Breadth first, I'm always exploring the next equal length option. And I just have to keep track in that queue of the things I have left to do as I walk my way through. What about weighted shortest path? Well, as the mathematicians say, we leave this as an easy exercise for the reader. It's a little unfair. The idea would be, imagine on my edges, it's not just a step, but I have a weight. Flying to LA is a little longer than flying from Boston to New York. What I'd like to do is do the same kind of optimization, but now just minimizing the sum of the weights on the edges, not the number of edges. As you might guess, depth first search is easily modified to do this. The cost now would simply be what's the sum of those weights. And again, I would have to search all possible options till I find a solution. Unfortunately, breadth first search can't easily be modified because the shortest weighted path may have many more than the minimum number of loops, and I'd have to think about how to adjust it to make that happen. But to pull it together, here's a new model. Graphs. Great way of representing networks, collections of entities with relationships between them. There are lots of nice graph optimization problems, and we've just shown you 2 examples of that, but we'll come back to more examples as we go along. And with that, we'll see you next time.
Just got an email. Okay. Let's get back to the code. I'll have to leave in like 2 minutes for my class, but after that, I'll definitely, because for this we're doing depth first search, and I know we have a couple of problems fundamentally, so we can look into that. Spider, there we go. Okay, let's see. So what are some problems? Well, the first thing is we don't wanna do this. I mean, this is just wrong. We don't want a tuple, right? So it's gonna be something like path.append total, and then we can do path.append total underscore outdoors, right? Okay, it's 10:45. I gotta leave now, but I'll definitely look into that later. Okay, let's. What happened here? There we go. Okay, nice. So we still have. I have another class at 2:30, so we have some time, right? And let's try to knock this problem set out, right? Okay. So we looked at the DFS thing. Now let's see. My coffee is like insanely warm right now. Okay. So, based on what we just did, the problem here is for some reason we aren't able to recognize total here, even though it should be, in my opinion, it should be, because this is part of the global, so we shouldn't even need to do the whole global thing, right? Logically speaking, this should just work. But apparently not. Okay. So and we don't want to break, we want to continue, so we don't want that iteration, but we want the next, right? And then we want to do something like if E not in path, right? So if we haven't explored it yet, so I'm clicking a picture of the lecture slides so that I have access to it. Right, so if best path if that equals none, or my best distance, right, is, we're gonna look into that later. I don't understand, maybe I have a misunderstanding of how Python works or how variable works, but I clearly remember if we define a helper function in there, it has access to the functions outside of it, so I don't know. If that is, if that is greater than our total, right? If that's the case, then new path equals to, so let's name this DFS because that's what we're doing here, and I feel like that's better. So new path equals to, we go over the graph, right? Our start is our end, so E dot get source, right? Well, what is E? Get underscore name, that should be it. E dot get underscore name, comma, our end is the end, we have our path, right? So we're gonna, actually it's gonna be path at first, so path comma end. Let's just, I feel like we need all of these in the end, right? What do I think about it? Our path is our path, and then our max underscore dist outdoors is never gonna change. But we also need the end, so end, and then our best distance is gonna be best dist, and then we have best path, right? So we call that, and then in here we'll do if new path is not equal to none, shortest or best underscore path equals to new path, right? So this means we need to change something. In the base case, we're gonna do return path. So it returns the path in the end we return best path. And in here we also need to do right. And in here we can start off the whole thing, so we can do path equals path plus Now it's just these two. For some reason, I still don't understand because we're defining our total outside, right? But let's see, there may be a better way to do this. Yeah, we don't want our total to be vanished. Return path, we can set all these to be 0. Let's see. Okay, so I need to use non-local. Okay, so if I do this non-local total and then non-local total underscore outdoors, okay, let me just do this non-local total there's a typo here. Okay, let's see where we are at. Which line? Line 147. So I think I only need, I don't get it. This is wrong. I didn't know that. Yeah, well, we can definitely do this. Have these ones at the beginning, and then this means always use that, right? Okay. List object attribute has I see. So so we can just do this e dot, what was the thing, get underscore name, right? what if we do this? Okay. No, this is wrong. I knew this was wrong, but let's try to think about what's happening in here, right? Try to I swear, finishing on pset is so relieving. Okay, so first we get a, I'm just gonna share Safari as well. There we go. Okay, first we get A11 8, this is 8, okay, and then we get a I'm just gonna put 5 here, 5, well, we actually get this is kind of incorrect, we get AB 11 8 and AC 5 2, right? So this is just like edges equals to, okay, and then for edge in edges, so for this one, S equals A, E equals B, the node B, right? Because get destination returns as the node. T equals 11 and O equals whatever. Okay. Well, we can suppose we can, so not in path, if node E not in path, so we have some path here, right? Also I have some of the code here. Okay, so if the node is not in path, there is something called has node, but that is for the graph, that is for that specific object. So in here I'm creating a list, right? The problem here is it says list object has no attribute name. So for my path, what do I have? I have an empty list. So it makes more sense for me to do this. Let's forget about if we convert s dot get name, get name, and e equals e dot get underscore name, right? If e not in path, so this is getting the string, and then what if we do now, str object has no attribute get name. Yeah, it's because we don't need get name now. We can just put in e. Oh, my boss is texting me from work. I'm not supposed to be in work, so let's see. Okay. 1 second, guys. My boss is texting me. I gotta fill up some form. Teams. Whoops. Let's see. Teams. Okay. Sign in. I gotta fill it up ASAP because this is for. I got a form for next. So I work for the university. I got a form for next semester's schedule whenever I want to work. So the earlier that you fill out, the better. So there's that. So I entered with the wrong email. I entered with my university email. I need to enter with my work email. Okay, there we go. Authenticator. What? Okay. I shall be back. Okay. Toot, toot. There we go. Let's continue for like an hour, after which I feel like I'm gonna stop streaming. Let's see. We're on this. Okay. So interesting. So this compiles. Right. So you get. So we do get what we wanted, but not just. Yeah, I think problem here is this. If we do this, okay, yeah, because this entire path is just a list. Correct. So let's try to. Whoops! Did I dox myself? Nope. Okay. So let's try to. Let's try to see what's going wrong. We're definitely closer, I would say. So okay, we have AC52 at AB11 8, right? Okay. So we get the name, and then total equals 0. So for AB, the total is actually the short for AC was 12.2, right? So let's actually do that. So it was, so let's see, this is 10 9, and then this is 12 and then 2. So we don't care about BC, honestly, because we need from A. I mean, we do care about BC. So the shortest path is gonna be 11. This is longer, so it does give us that. It is 11 and 10. So this calculation is working. So we just need one, like we just need something like A comma B 11 comma 10 instead of the way it's being formatted right now. So I guess formatting is what we need to fix. But let's see how to do that. So okay, AC52 instead of 52 it's gonna be 12 and 2. Okay, so at first my total is equals 11, total outdoors equals 8. Okay, so 11 and 8 at first. If so, this is never gonna happen. We don't need this line. We just don't, because this take care of that. Yeah. Okay, so now let's see. So my path is initially this, right? So what I'm saying is there's clearly something wrong here, because I don't want to add this thing back to the start, right? What I do want to do is so what I do want to do is path 0 is gonna be dot append e, right? And this is gonna be if e not in path 0, path 1 dot append path 1 dot append equals total, and path 2 equals total underscore outdoors, right? Now it's doing BC 1110. So the 1110 is, it's working, but I think I know what the problem is. Let's try to run through this quick. We're so close right now. We're actually pretty freaking close. So it should be ABC, not just BC, right? Because we're not appending the start and the beginning. So if we just do this, path 0 append start. Yeah, that's a bummer. That's not what we want. Yep, I knew that's gonna be a problem as well. Let's not just guess and check, and then, let's actually try to. This should be interesting. Yeah, guess and check or whatnot. I mean, clearly not a bad thing to do, because actually we do need that line. It should be break, right? Clearly I broke something here. Okay, so clearly it didn't like break. And now I don't know, I guess I broke something somewhere. Okay, so that line is what's breaking it. Because even if I do, I mean, it's not like this is gonna go anywhere. It's because my total starts at 0 now. So I guess we can easily solve that. Infinity in Python. Yep, if we just do float infinity, and now if we do total greater than best underscore dist break. I guess I need to import math for that. Yep, because this, oh, I think it's just this. Yep. Okay, buddy, why are you not working right now? We comment you out. Yep, you work now, but we comment you back in. I refuse to believe that my best. Don't know. The only way we can do it is if we run through the code again, right? Because well, let's do this. Okay. So that's what I'm thinking. So it reaches here. So my total is 11 so far. It's 10. Yeah, it's 10. So my graph is my total is 10 so far, right? Okay. And it goes here. It finds all the edges for B, which is basically C, right? And then my total and my best dist is equal to my total right now, right? So my best is also 10 and my total is also 10. So if total it's not greater than best, right? So in that case we this is clearly wrong. This is where I should put this. There we go. There we go. Okay, ABC 1110 looks okay to me. Now we can move on to the next problem, I guess, but I'm gonna ask Claude and see if it thinks it's okay. So Claude says that there's plenty of things that are still wrong with my code. Fair enough. I mean, I was using a very small subset of test case. I can imagine that there would be things that are wrong with my code. If I hit a dead end, for example. But let's try to tackle one issue at a time. So this is the input that Claude gave me. It says there's a problem with the backtracking, the break statement is a problem, and then my update, the way I'm updating my best distance is also a problem. So let's read it one by one. This is a key concept in DFS. When you explore a path and it doesn't work out, or you finish exploring it, you need to undo what you did before trying the next option. You do path 0.append start at the beginning. But when you finish exploring all edges from a node and turn back up the recursion, does that node get removed from path 0? What about total and total orders? When you backtrack, do they get restored to the previous values? Think about it. If you go to A, B, C and it's a dead end, and try A, B, D, you're about to explore D. Interesting. Okay. We can use this example later. But at least we have something working. Let's try to draw a graph like this. And then, so this is directed, and then we have D here. Okay. Right. Okay, now let's see. So based on my code, let's say this is 5, 4, and then this is 10. Okay. So based on my code, I don't really care with outdoor values for now. We do path 0.append start. So start off with A, comma 0 comma 0 or none, whatever. Start is not equal to end, so you get the edges. So we get AB5 and then AD10, right? Okay, total is equal total plus, so the first one is gonna be this one, so total equals 5. Okay, my best distance is right now infinite, so is B in path? It's not in path, right? So we add 5 here, and then I'm gonna look about this with best path, so we don't have best path, and my best distance is infinity right now, so it's definitely greater than total. So my new path is gonna be DFS on this. So let's, and after that I need to have, so I'm gonna, so this is a call stack, so after that I have a couple more lines to execute. My best path is gonna be my new path basically. So let's go up. Now we're calling it on B. So my path is this right now, and on my path I'm gonna append B here, so AB, right? And then comma 5 comma 10, my start is not equal to end. And then we do the whole thing. We get our total to be 9, in this case 0, and it's still infinity, so we do another DFS. We have some lines of code here. Okay, for the other DFS we add C here, A, B, C. We do, actually I don't need to do the pop thing because we're gonna go up this call stack, so I think the first part is okay if we end up with a dead path, but I might be wrong. Let's see. 5 9, I think I've messed up somewhere. C actually doesn't go inside this loop because it's a dead end, right? So since it's a dead end, it returns us the best path. And for C's case, the best path is none. So it propagates up, and then in this case, the best path is the new path is none. So the best path, it's gonna propagate up and it's gonna return a none. So for B there was nothing left to explore, right? So for A, this line is not, it's gonna go back up the loop and then it's gonna start exploring AD. So I feel like for the first part, I'm making AI smarter as I coding along, right? But just to the recursion, am I not really doing? But it's being passed into the parameter, right? Let's just give okay. I have a feeling that I don't know. I guess there will be something wrong with my code, but yeah, there's definitely this didn't give us anything. So clearly, oh, of course it didn't give us anything because there is no path. AB 10.5 exactly. ACB is a shorter. 5 plus 3. Okay. So let's see. This is a harder test case. What was it? Start is A and end is B. Yeah. It gives us ABC. Okay, so there's clearly something wrong. I mean, not denying that. Let's see. ACB is the shortest one. Where are we getting C? I have no idea. Right? Because we shouldn't get C. Yeah, there's clearly something wrong. Let's see. Okay. Maybe Claude is right. Maybe I'm just dumb. I mean, this is pretty good debugging practice for me, so I don't mind. As long as I can done with this, then maybe feel like I'm chilling. Okay, so node A, node B, right? We have my dog screaming. Node C, and then node B. So it's a triangle. So 10, 5, 3. So the fastest path is ACB, 5 and 3, of course. Let's see. So should be 8 technically. So I get a B10, a C5. This is one call stack. This is my iteration I. Now in this call stack, I have path 0 to depend, so my path is for now A. Okay, if I need to pop something, it's fine. But let's see. So because in the lecture he didn't pop anything, or did he? I don't know. Okay, so we have A right now. I mean, he did for BFS, but not for DFS. So if E not in path, so E in this case is B. So clearly it's not in path. So total is gonna be 10. I don't really care about the outdoors from now. If best path is none, which in this case it is, my new path is gonna be DFS and then some code left to execute, right? So let's go to the next call stack. And this is passing in this as the path variable. So what I think Claude is saying is that every time I'm going to the path variable, I'm modifying it, and it's gonna persist. There's a whole thing of mutability versus immutability. When I'm adding that B, it's gonna persist, right? So if I do this, pop, there we go. Not really. It's not really AC. It's ACB. It has to end in B. That's the whole point. Let's keep at it though. So now I have A, B, right? For B, we cannot execute that because nothing goes out of B, right? Nothing is going out of B. So return best path. So new path equals none. Yes, and even if we're gonna do this, then whoops. Well, what is happening? Holy, there we go. Path, because even here, oh, not append, pop. Now if we do this, we get nothing. Oh my god, I clearly did something wrong. What I was about to do is, this has AB right now, right? So since this is AB, it goes back up. So I was popping B out, right? So I was popping B out so that it starts, it stays at A and then we explored the next one, which is AC, right? Before, right? So let's see what's wrong with that. So let me go to the bathroom. Clearly, this isn't doing what I want it to do. Not at all, to be honest. Okay, well, let's see. We're at AC 10. So we turn a path. You see, now where am I going wrong here? I have no idea. This definitely looks more correct. Way more correct. Okay. So we have let's keep at it. Let's see what mistakes we have. AB 10, AC 5, right? Okay. Our path 0 in this case is A for now, and then not none of this executes if E not in path 0, path 1 equals total. So it's taking a long ass it's time for me to finish. I'm so dumb. Total plus D. Yeah, so 10, right? And then we go to B. Some lines left to execute. In B, we don't have anything. We add that to our path 0. So new path is just returning us none. So we go here, we go to C. And for C, we can activate the new total, which should be 5, right? It should be 5. And then C has a couple of. C has a B. So still 5. So A, C, I need to trace through this deeply. And we're so behind. I wanna at least finish this problem set today. And then we can worry about some other problem sets later. At the very least, I want to finish this problem set today. Well, let's see, I don't think so that's possible. That's fine, we can do it tomorrow, I guess. How far are we into syllabus? I did till random walks is 15, so we still have a lot more left. Okay, let's keep at it. I wanted to use some sort of debugger. However, I don't see any way I can do it with the number of. I don't know if this has its own debugger. Does it? What is this? Preference, Python path, profile. Okay, so debug. Let's see, how does this debug work? Do I press enter? How does debug work in Spider? Okay, so I can. Let's see if this is if it has its own debugging method, then perhaps there's some hope. What is happening, bro? Please, I want to debug this. This can be my breakpoint. Debug file. What is this? Okay, so this is where it's starting, bro. I don't want to start there. I want to break there. Execute until next breakpoint. Okay. Step into function or method. Execute until function returns. Okay, nice. This is what we're looking for. Yeah, okay, nice. This is what I care about. Cool. Total equals, where do I see variable explore? There we go. That's what I wanted. Nice. Okay. So path is at first A, right? My end is B, so there is no. Sure. Okay, so we get a couple of weighted edges. Oh my god. Okay, we get a node object, that's fine. This is T is 10, nice. And then we have our S equals A, and we have our E equals where is E? E equals B. Nice. So my total equals 10, right? And total outdoors equals 5. That's not the case. Oh, this is overpowering. Holy. Okay. Path 1, path 2. Okay, so we have 10 and 5. Exactly how we expected. And now let's step into the functions. We have, okay, so we have path, so we have AB right now. And it is equal, so my best distance, which is infinity, is now 10. Total equals 0, and my total outdoor, and I return the path. My path right now is AB 10 5. So that's one path. So this is one of the path. This is my best path so far. It's the only path that I saw. So I pop the first A, the total equals 0 in my, so now I wanna go to the next path. I have a feeling it's a bug in the total calculation. We should do total minus t, but we'll worry about that later. So now it is so. Interesting. So empty. I'll be back. for me to end it here because I have class and after class I have work. So, and by that time I return, I'll be tired as fuck. Hopefully I can solve this entire thing tomorrow with a fresher mindset, I guess. And then let's see what happens. But yeah.